So, in this lecture we will look at, so we looked at regenerative code, local reconstruction code, and also this what is called the very important thing is the bandwidth storage trade-off in distributed system. So, when we did with regenerative code idea with the information flow graph, sometimes we kind of agreed that we had a theorem, and from there we just brought out this issue again. But can we look at the same information the bandwidth storage trade-off from information theory perspective, because I think Adrish gave you the talk about information theory about basics of randomness and others, and that could be used to. So, once we understand that and model that through, so maybe we can understand the parameters a bit better. So, that way we can understand what is MSR and so forth. So, let us bit very clearly and at the end of this try to understand this topic. Our goal is to just to go through the a perspective from information theory, and you can have a similar proof. That is all the thing is the goal. So, as I mentioned to you in the first thing itself, as a regenerative code based. So, now you will, as you go through now, you will start seeing the interplay between the various parameters that we use to define a code. Now, for example, with initially we start with a coding theory. We say you have a length of the code, information symbol, the dimension of the code, then you have a minimum distance. So, now we looked at within Reed-Solomon code context, or in the storage context, we had and introduced something what is called as a something that you store in a particular node, and also for repair you actually derive from a particular node. So, the idea of alpha and beta, the two parameters, and so probably everybody is now aware of it, but let us try to go more very clearly and through that. The first one is that as you can see that in original data n bit you can take n alpha. So, the actually file that you want to store can be divided into n times alpha symbols and then distributed across n nodes, and these symbols can be drawn from finite field FQ. So, we will make it a FQ, and then each node store alpha symbols. So, the basic features of regenerative code you can say is that first, any k node, the original data file can be retrieved by k out of n, and also regeneration is any failed node can be recovered by permitting new node to connect any of the D helper nodes. Now, in the actual Hadoop implementation, you saw how, for example, a particular node when it is down, you can see the system's point of view, the complexity is involved. Now, we are actually modeling all of that, and we think is that in the code now the failed node has to connect to any of the D n minus 1 surviving nodes and to recover it. And now we so what are the problems with k and n, how they are do, and so regenerative code with nkd beta has to achieve this trade-off bound. This is what we said in the first one. Okay. So, I will go through the same thing, but from information theory perspective this time, same bound. So, that means the maximum size of the file that I can safely store in the system with this code is always constrained by summation from I equal to 0 to n minus 1, minimum of either alpha or d minus I plus 1 beta. Okay. So, this is this part of this. So, most studies now focus on actually two extreme points, one is MSR and the other MBR. So, this will tell you why they are focusing on it, because in case of MBR codes then it is the bandwidth is minimized, and so at that time you may have to store more per node, but when a node fails then you will actually download less, and so that will improve the repair process. But on the other hand it requires more storage per node, whereas when you have a MSR code it was more like where the storage is minimized, but then you can also, for example, minimize the number of bytes to do on that, but you can get a the both point for alpha MSR and beta MSR. How did you obtain this? So, do you all now clear about these points? Yeah, do you know how this comes? So, for example, when MSR, So, basically it is a minimum storage code. So, any k node should have that information. So, size of every node should have at least beta divided by k. But then how is this is true? Okay. So, we looked at it, from that there I gave a proof. So, you first in the process of regenerative code, what you do is you actually express with respect to both alpha. So, I can't minimize both. So, once you actually minimize alpha first and then minimize beta to get those points, and similarly you minimize beta first and then minimize alpha corresponding. That is what we did in the things. And for proof of that, I suggested you to go through the book, the paper by Demarkis et al. So, let us look at this one, we will see whether we can follow this today or not here. So, and this is just kind of explaining the trade off bound, and we will try to do that. So, here we will come now, we will try to look at the model. One is definition is for example here entropy of a random variable x. So, entropy of a discrete random variable x is with a probability distribution. This was given by in the thing. So, for example, you take px times log px minus. So, it is actually px times 1 over log px, that is the entropy is defined as a reciprocal to the probability occurrence of that, and you have heard about that is why Adrish gave a special lecture just to make some of these points very clear. So, this is basically treating a particular. So, what in our case what we do, we take this contents of this node. I do not know what we are going to store in it. For example, file can be anything. So, what you are going to store in a node can be anything. So, like just as you can see that in the stripe case you have so much of information. So, maybe I'll erase all of this. So, that can be viewed as a random variable. So, we do not know. So, it could be anything. So, using as a random variable, and then you can define entropy, which is a measure expected uncertainty from in x, whatever that. It has a property that is always h of x greater than or equal to 0. We looked at the properties of that. There is a Hartley entropy, and this is a Shannon entropy. And the rest of the other calculus that we use to play around with the things we discussed, and we will probably use it a little bit. And so at least so that way sometimes to understand some concepts in it, you may have to go back into that lecture to go through. So, joint entropy and conditional entropy. So, same joint entropy between two random variables and the condition entropy within random variables are given by appropriately. So, the entropy of x x comma y is you actually define over the joint variables. So, you over joint you take expectation over joint summation over joint distribution times 1 over log px or minus log px will give you that. I think this is quite clear, right? And similarly, the entropy of a random variable given x is on the other hand also same as this expression, which is which given by probability of x happening and the entropy of y given that x equal to the particular x, and you take sum over all x. So, this is the conditional entropy. So, joint and conditional entropy now provide a natural calculus that we looked at it. For example, you have a joint entropy between x and y is equal to entropy of x plus entropy of y given x. So, that means so if you have two random variables x and y, you want to find out the joint entropy, you can use this formula to easily compute. So, then another concept that we will use is mutual information, which is just exactly what we did before. I am just covering them for the purpose of this lecture. So, mutual information and conditional mutual information. The mutual information between x and y given another random variable z, the conditional mutual information between x and y is respectively given by these formulas here. So, for example, mutual information x and y is what is the kind of the mutual information there. Intuitively you can say, for example, the entropy of x minus the entropy of x given y, the variable conditional y. So, if you do this, you then of course you can, there are ways to define this sum and compute it. And similarly, y mutual information x and y conditioned on z is same as mutual information x conditioned on z minus you can actually do it like in this form. Okay, this you can use. Now, advantages of all these things is the chain rule, which was mentioned at the end of the the Adrish lecture. The chain rules for entropy and mutual information are basically you take the entropy and you now create it by using. So it allows us you use the chain rule formation. So if it is a entropy of x is given as all other elements, and you can keep on adding this and create this, and similarly the mutual information rule you can apply. So having approved the basics of information theory there, now we will look at the information theory perspective of this code. So all data symbols including data stored, those are sent from the helper nodes are treated as random variables. Okay. So here so each now for example all the nodes, so we will now represented by a random variable wi. So there are exactly n nodes. So you will have to probably bear with me when I change the notations, maybe the indices I might move around, but at this point without loss of generality I can take that I is one of the n nodes and wi is a random variable represented by that corresponding content in the node I. So wi is a content in node I. And so now what is happening is, since each storage node has a capacity alpha, so that means it has alpha symbols in it, I can say that that's the maximum it can store, there is only alpha. So the entropy of that particular random number has to be less than or equal to alpha. Is that clear? So it is just intuition, straightforward intuition here. You can do that, and similarly I can now have a set of variables wa. Now a is a subset of 1 to n, so 1 to n is in numbers from n. They denote set of all random variable corresponding to nodes in a. So they are all set of random variables. So here is the repair data from node I to j. So this particular, so you understood this kind of a modeling of each thing with a random variable, that is very important. And I actually follow this from one of the Vijay students paper. It has come out very nicely in explaining these concepts, and in fact some of the MSR point as well. So if you are not very careful you can easily mistake, and then you do not know why the answer is wrong. It is I will tell you, you can go through some interesting, but even yesterday night I thought after finding this and I found the equation, so I mean it is not adding up, it is not coming out the correct result. So then I had to add this thing carefully to do that. So let me explain this. So here the storage node now, so you have got W1 to Wn, there are different storage nodes are there. Now what is the repair thing? So if you are repairing, you get some other information from another node, right? So now we are trying to model that. So you see this is a storage in each node, and I will now invent another random variable, okay, which is s. It has an index I and a superscript j. So what Sij will tell you is the amount of information that is downloaded from node I to node j. Whatever that purpose, I now model that as also a random variable, because this is a random variable. What that goes in that is also a random variable. This is fair, right? Yeah, so far it's fine. So now let Sij now belong to one of these nodes. I not equal to j, of course you can't that is the kind of thing, is denote a random variable corresponding to the data symbols sent by the helper node I to the replacement node failed node j. So another replacement failed node j, this is the information. And data pipes, whatever that it goes is you only download beta, because that is the model, right? You take a beta information from every failed node to recreate. So obviously the entropy of that one has to be less than or equal to beta, correct? So you can't be more than beta, okay? So now SAB now, and also you want to say, because let us say when you are repairing one failed node, for example J failed node, you might get beta from some other D other numbers, okay. So now idea what we need sometimes in the proof is that you actually put all those random variables that are used to repair J. So I can get, so this basically this idea. So here there is a j node and all the other nodes here I put it them in A, set A, okay. These are the set of nodes, the D, what is the size of A? Huh? No. So here I mean set A denote, here I say in general of course the definition here, but let us say when you are down repairing this one, this will be generally you contact D, generally it is D, right, repairing you contact D, but this definition I take it for any two alphabets. So you take beta download, okay, and you repair it. So this is what you do. SAB denote the set, that is Sij. Now I belongs to A, that means all the elements in one set, and J belongs to B, another set, I not equal to B. So A and B's are subset in it, and particularly this is how it is done, okay. So this particular, I mean there is not this is just to kind of to have a set of variables. Now these set of variables actually all these variables are dedicated to repair node. Which node? Jth node, very good. Yeah. So now J could be from one set of node, another set. This is just a pardon? Yeah, that's oh, okay. Just tell me why. Huh? So this is when B belongs to all of that, A, so for the B is some subset of that. Now the other one, A is 1 to n plus 1. I thought just look, why D plus 1? Huh? There are D nodes. So it's just that, for example, particularly SB substitute for in case, so this is okay, ignore this. I mean in case if you use SB, that means it's this should be for any D. So sometimes it's all in the, when you are taking in a row there will be one extra thing, but doesn't matter, it's just a definition now at this point, okay. If it comes I will tell you. Okay. The two basic properties of regenerative codes now translates as so this is the reconstruction now. You need to write one n away, okay. The reconstruction property. Let's look at now we will look at the regenerative principles, and they said if for every subset A of nodes size k, we have that the message, really the file message, the entropy of message given that particular k, that should be 0, correct. That means any you have got a MDS property, that means you take about any k node, yeah, is that clear? So let us see whether we can understand. For every subset A of nodes of size k, we have that h of MA is equal to 0. This is the entropy given condition A, that is equal to 0. Okay. Now exact repair property is that, now let us take D belongs to 1 to n, okay. So now you take a particular subset of 1 to n, minus L means it's not equal to L, so I not equal to all other elements, and of course size of the D has to be D. So the set of D helper nodes in the exact repair node is if you have there, then we have that the entropy of WL on condition on that all those random variables, that's 0. That means if this is basically what's happening is that a node can only, so this just take out the exact repair property again. So we'll look at the exact repair property. So you will you will look at the D, the set from D. So basically, yeah, so node is repaired and you contact D of them to other nodes, and that set is D. D set is exactly D, and L is this one, and L is L is not in that set, so it is subset of that. Then WL is the for example the information that used from SDL. So basically all these D information bits beta is used to reconstruct it. So after it is reconstructed, it couldn't have more than information what these random variables provide, right? So this has to be, if I look at the entropy of that random variable WL given all other random variables that are used to repair them, that has to be 0. So these are all I am just applying from the requirement of regenerative code. Okay, clear? So furthermore, so these two, any clear? So yeah.
Sir, the notation in the second bullet, WL given SDL.
Yeah.
L is equal to 1 to N.
Yeah.
L is equal to 1 to N, but what does it mean?
Oh no. So no, this is what I am saying is that this is for all L from 1 to N.
Okay.
So that means whether you are repairing the L is, so let's look at this. Is, I think yes, but I tried to kind of uniform. I had two set of notations. So you got all 1 to up to N. These are the different nodes. L could be any one of them, right? And I have defined D to be the set without that. So when I look for this SDL, is obviously you are looking at the variables that are D elements, but that is not equal to L. But now there are this L is of course going from 1 to N. So that means this is true for every L from 1 to N.
It means there are N distinct equations.
Yeah, N distinct equations. Okay, that because that's how it is. You are allowed to repair anything. So that's what you saw in practice also, right? So these are all just when you do this is the same.
Even for a fixed L, SDL is basically S1L, S2L up to S small d of it.
Yes. Yeah. Oh yeah, actually very good point actually. What he said, what is SDL? We defined SDL is what? Is a set.
Yeah.
So that means that set of variables that is given one variable, condition on that set of variables, that entropy is 0, because only that has all these variables have recreated this. So obviously this variable has no more information than what these variables have given to it. So it's only modeling that thing, right? So furthermore, now this is another interesting thing you see. Now you take about any node can only pass information what it has. It can't pass something different than what it has. So let's take about some variable number m, for some m. In fact, I should say this is true for any m, for all m, you can have, and let us say this is the variable that is taking from m to L. So this is a particular, so if this is one of them is L, and this is in this case is only 1 to 1, like there is L and this is so this one of them is L and this one is a WM. I mean it will be one of them only, right? Just I am taking the beta, this can only pass beta, right? Each time it is there. So whatever that whatever SML is actually the random variable for this particular whatever the contents, that can't have any more entropy than what the node it gives, what the node it then where it is sourced. Like so obviously WM is 0, so H of SML comma WM is 0. So these are I only used basic things, nothing more. So continuing, so we will start applying on all these things here. So, any node L now has information pertaining to the message M, and a node can only send data which is a function of its content. Okay. So, this is basically the, if I look at that one, the same type of thing, that is the entropy of WL given the message is always 0, and H of SML given M is also 0. I mean, any variable there, it is actually part of the message itself. So, this is straightforward. Now, we can write the reconstruction property of the property 1 of previous slide, the reconstruction property, that H of MA for 0. It can be that now you take about all the set of variables Wi to k. And I could also write this particular expression. I was not lazy to write one more slide like this, with the notation that we have done. What I have done it here is H of say I take now is a set. Now, set can have from I equal to 1 to k and W Li. So, sorry, it is just Wi Li. So, I equal to 1 to k, so all the variables, and that is equal to B. And you can see that previous this property, in fact, every subset of k node has the complete with the message information. So, that should actually completely represent the finite field. So, I could also write this as a H of W. So, there was another thing that I used, W for example A here, yeah. Sorry, W A here, yeah, that is and A becomes to any of thing, that is also B. So, W A means basically all the variables, any k variables. Yeah, not joint entropy, it is just yeah, all the joint variables in the k, any k nodes should have the whole information. File should be reconstructed from any k. So, that is the way to do it. So, the first lemma, this is given actually in the paper by Shah and Rashmi and Vijay Kumar's students. They distributed storage codes in repair, transfer, non-achievability of interior points on the storage bandwidth trade-off. So, it has a much more detailed discussion on the the storage bandwidth trade-off curve. So, this is so now this first lemma that is mentioned in the paper. So, you can also go through, that is this: consider an arbitrary node L. So, take an arbitrary node L, an arbitrary subset A of consisting. So, now what I do basically to do that. So, remember, even in the previous information flow graph, we would look at it, the min cut we would do only if for example you always choose if alpha and d minus that one is whichever thing is minimum, you will include in the min cut. So, in order to get a final thing, it is a similar thing will come. Now, probably we can understand a bit more with this modeling a little bit better, where let us say now consider an arbitrary node L, then I can take arbitrary subset of A. Now, so A of size now a small a, okay, and then also and consisting of A, and A is between 0 to A to D nodes, such that L does not belong to A, okay. Then the entropy of WL given SA of L is always less than or equal to min of alpha minus D minus A beta, okay. And hence you also say this is due for any. So, what is the SAL is all the variables in this WA. So, this is what and hence H of WL given WA, all the variables in the set A is always less than or equal to min alpha into D minus A into beta, okay. This is the statement of the theorem, okay. So, how do you prove that? So, this is we shall look at the exact repair. So, now I mean for in the paper, if you go through in detail, they also do it for functional repair. Similar thing can be done, but exact repair is probably easier to see from the information theoretic in the purpose in the beginning. So let us look at the exact repair of a node L by connecting alpha nodes in set A. So it only connects alpha nodes in set A and d minus a other arbitrary nodes. Okay. So now denote the set of d minus a helper nodes by B. Okay. So now set A has a alpha nodes in set A and d minus a sets are arbitrary nodes. So in some sense what happens is that the set A has kind of those nodes that actually contribute to alpha less than or equal to alpha. I will come back to that, but so denote the set of d minus a helper node to 0. So then I can write down this as the you can see that what are the things who are doing, they are trying to actually repair nodes. So by connecting alpha nodes in set A and d minus are the alpha node other arbitrary nodes. Okay. Yeah. So this is possible, you take alpha nodes from set A and d minus a other things. So what you can say, this implies that you can look at the entropy of WL condition on the variables SAL and SBL. Obviously that is true because it is repairing, that is true, right? I am applying a general reconstruction thing. And then so then this I use the information theory calculus and write this as, this is same as the entropy of Wi given SAL minus the mutual information between WL and SBL given SAL. Okay. Is that clear, that portion, this step? Then after that you can actually you can write that this one, this is basically lower bounded by the information theoretic means. So if you have if you are looking for the mutual information between WL and SPJ given that, is actually lower bounded by the entropy of SPJ. Remember one of the theorems that Adrish did. So then but that's I am now lower bounding because this is an exact one. If I only take the SBJ, the entropy of that, so this value is always greater than or equal to this value. So yeah, is that clear? So you can look at the paper in that one. Correct? First line. We shall look at the exact repair. So what I am saying is the connecting alpha nodes in A and d minus or should be, sorry, it should be A nodes in set A, so it's not alpha, sorry. Okay. So you correct it out, that one. Okay. It's A nodes in set A and d minus A in other arbitrary nodes. So I make the two set, right, and denote the set of d minus helper nodes, and then this implies this. So this one I am just making a simple lower bound which says that this mutual information is greater than or equal to this. Now coming from this to this, so you say that since d minus a helper nodes in B can pass at most beta units, because we have taken the A units actually give you alpha units, okay, alpha units of data, and d minus a will give you beta units of data. So this will take d minus a helper nodes will give at most beta units, sorry, at most beta units of information. So obviously you can't this can't be more, the HSB is basically d minus a times beta, you can't be more than that. So still this is there, and now what I can do, so this basically lastly the last equation now follows, since a node can only pass function of what it has. So you can't this can't be more than whatever that it has, right. So the last equation. So this implies that so you can see that h of this node, that is all the W h of WL less than or equal to alpha, this is basically is also there. So you have now apply this into this. So, this particular node has to be either minimum of this or this. So, you get back into the leading to the desired result here. Okay. So, this is the result. So, arbitrary node L, yeah. Can you is that clear now, the steps here? So, this probably I had to do one more change because I think I copied down and making. So, there is no, you see there is a no change from this step to this step. What should be, what is the problem? Huh? So, when I looked at it, yeah, and in fact this should be not this should so you can see that this is same as this, right? And so so I have here I have SL, I have so this I had to change the last equation with the following thing. That's the mistake thing that is in the code. So you are clear up to this point, right? So this is just the lower bound. I take the mutual information h of SB dash is SBL to be the mutual information. So this has to be greater than or equal to this value, and so here obviously h of L b, so SB whatever that goes from B to L is d minus A times beta. That's what that's the size of the set beta, okay, and it can only give beta elements there. Now this one, but this is same as, you know, this is the H, this is equivalent to S of A comma L, S L A, you can say the S superscript L and subscript A. This is same as, this should be greater than or equal to H of W L given W A minus D minus A times beta. Do you see the point? So this is the, you can see that this one comes because each node can only give at most beta units, but this is same as because whatever SAL, all these elements, you know, whatever that come, these are all the contents in the variables in set A. So H has to be greater than or equal to WL given WA, okay. So beta units of information, and the last equation follows since node can only pass what it has, okay. And also what you can show is this is because you know, then you also know this, you for any, you take WL, H of L always less than or equal to alpha, because of the constraint from each node can have that alpha. So that actually completes that's the result. So you say that H of L comma WA is always less than or equal to min alpha. Yeah, is that clear? Okay. So once we have, you know, prepared with this lemma, so for example what it really says is that while repairing consider an arbitrary node L, the arbitrary subset A considering A nodes and other D minus A beta nodes, they all repair a particular node. So the entropy found in with a condition on those nodes in A that is always minimum alpha by this, because we showed that this is minimum of this. The basically what I am looking for is this itself. So if you, that is 0. So this is always 0 is greater than or equal to this. What does it mean? That means this should be greater than or equal to d for it to be. So for this to be greater than or equal to 0, here is 0, remember, it's all 0. So this should be greater than or equal to this, correct? For this to be greater than or equal to 0, this item should be greater than or equal to this. So the left hand side there is a 0. So this one, the entropy of this function, this has to be bigger than this d minus a times beta for it to be, for the whole thing to be greater than or equal to 0. Okay. But we also have the thing is that h of wi is always less than or equal to alpha, and that gives you, that is why this is this one is less than or equal to minimum of this or this. Yeah. So that is how the lemma is worked out. So based on this lemma, then you apply just the theorem. So for any nk d alpha beta theorem, a regenerative code must satisfy the following relation on file size. Okay. Now beta is a file size, that you have a message and message can be transformed into a file size. Now how to that is always less than or equal to beta is less than or equal to minimum of alpha minus d minus 1 plus beta. Now let us look at that result. Here it is just simply, now it is much more using the previous lemma, I can just apply to all other variables. So from the reconstruction property, what did we learn? So let us take the reconstruction property. Reconstruction property is, here we put here, that you take over the entropy of all the variables up to L1 to k is 0, is b the file size itself. Okay. Now so you say any regenerative code, the beta is h of I now consider the reconstruction property demands that the entropy of all these set of variables together, giant entropy, is b file size. Now that it can be written now by using the calculus what we do. So you take about I equal to this is equal to L equal to 0 to k minus 1, this should be Wi given Wa. Now from the previous expression we found that that's the lemma, that's actually is equal to min of alpha minus d minus beta, and you can put some I equal to 0 to n minus 1. So this is minimum of alpha into d minus I plus 1 beta. Okay. So now you apply the so the last equation follows from the lemma given below. So once you have a lemma, you just apply and get that. So what does it tell you? That the so for the trade off, so now we have proved the trade off that any file that you store it on a regenerate nkd alpha beta regenerative code must satisfy this particular bound. Okay. So that is the kind of thing. So I asked you a question at the time of regenerating, and probably now we will look at the same problem. So now I can start taking n, k, d, alpha and try to see how the parameters behave. The problem is that I cannot I can't minimize on both alpha and beta which is the bandwidth d beta. So I had to do one another. So when will you say that a particular regenerative code is optimal? Okay. So now for the point 1 we define like that. So let us say it should hold equality, right. So for it to be optimal, that should hold equality. So that is b equal to I equal to 0 to k minus 1 min of alpha times d minus I plus 1 beta, and if either alpha or beta is decreased, this should fail to hold. Like alpha or beta are such values that it is always b is always equal to this, but even if I try to change one of them, then what will happen is if it is optimum, that should fail. Pardon? No, I equal to 0 to k minus 1. Why I plus 1? So that's what I'm saying is whether, see, this is what I'm saying is which node I look at it in the things, that index doesn't matter. I'm only looking for repairing one by one. So here this is basically for each of them you use that's why I said the indices are doesn't matter really, because it's only the size of those sets that participate in the repair. So here so that's why beta is 0 to k minus 1 into alpha into d minus 1 plus 1 beta. This is what we proved as well, see, look here. Sorry, this is the result that we will do, right? I equal to 0 to k minus 1, it's either minimum of alpha or d minus I minus 1 plus beta. Okay. Okay. So this is the file. So for fixed value of p, NG is optimal if equality holds in the trade-off, and if either alpha or beta decreased even a little bit, then this equation doesn't hold. The endpoints now can be obtaining evaluating. So this is where I wanted to go, and so probably I haven't given these things in the things, and let's work out the endpoints of the thing. So for example, I will take the minimum storage generating point. What you want is that we want to, so alpha has to be, so what you notice is that let me write down these equations here. Okay, that's the optimality equation. So now note that when alpha is less than, so what happens, what are the values that this can do, I can go, I equal to 0, then you can substitute I equal to 1 up to I k minus 1. So when I equal to k minus 1, then this is d minus k minus 1 times beta, right? When alpha is so this is k I minus of I, which is when I equal to k minus 1, which is d minus k plus 1. So k minus 1 plus 1. So this should be plus 1, right? Minus 1. Yeah. So this is plus 1. So when I equal to k minus 1, what will happen? Let me check. Think I equal to k minus 1, d minus k plus 1 so just what d minus, sorry, so basically I wrote this equation wrong.
Actually, a couple of days back when you were teaching the local regenerated codes, you had a similar equation where there was e minus I on it.
Okay. So basically, in fact, this, the thing is that what I was trying to do was actually, let's look at the thing where I'll correct it one by one. So this one should be, beta should be less than or equal to just d minus I. Okay. So we'll correct this. So now this is the problem. Everywhere it should be d minus I. I could have probably retained the indices. If it is I equal to 1 to k minus 1, then I had to actually add it, not otherwise. 1 to k, then I had to d minus k plus 1, that would be correct, but now I had to actually take it back. Sorry, actually this was my mistake I did yesterday, so please correct yourself. The first theorem itself is k minus I, okay. We'll probably I'll probably send the revised thing to everyone. Then this is all true, this is all true. Also in that case it's better to make all the indices 0 to n minus 1 as opposed to thing, but that's not a problem. Then you come here. So here you see I'm making d minus a here itself. So this should be also now beta is less than or equal to d minus I only, okay, not it's always d minus I, and now beta is equal to now I equal to, so this should be again 0 to k minus 1, and so this has to be min of d minus I times beta, okay. Yeah, d minus I times beta, this is also change the plus 1 to beta, and then we come here also, now the beta is exactly this, okay, d minus I times beta, it's very clear. So it's either alpha, minimum of alpha, d minus I beta. So when I equal to k minus 1, what happens? Then this is d minus k plus 1, right, times beta. So so you see alpha has to be, so when alpha, when note that when alpha is less than or equal to d minus k minus 1 beta, you can decrease beta without violating, because the alpha is already satisfying that. So alpha, which this implies that alpha has to be greater than d minus k minus 1 times beta, correct? So plus 1, yeah. Alpha has to be greater than d, so again I made, so while copying I made a mistake, so sorry, you have to be plus here, and alpha is d minus k plus 1. So once you get, so alpha, so when alpha takes the minimum value, so we have this, so this should be plus, please change over everything, plus here, okay. So MSR point in the can be written as now, so what in MSR point what will happen? So yeah, d minus k minus, so here also plus 1, right? This also plus 1, this also plus 1. Yeah, so that's why alpha has to be greater than or equal to this d minus k plus 1 beta. So and when alpha takes the minimum value, so obviously alpha equal to d minus k plus 1 plus beta. So from there you can get beta equal to b. So now alpha equal to b by k, then beta has to be b. Is that clear? Clear? So I think I was trying to play around with the notations, and yeah, it's just plus 1 minus 1. This can get you into trouble, then your equations won't get it. In fact, that's what happened when I tried in yesterday night. Equation didn't work. So now let us take the minimum bandwidth project. So here if beta is less, let us say less than alpha divided by d. Yeah, let us say if b. Okay. So in sense I can print it off and give it to you, but probably just quickly note down. So but you also need to make some changes. Okay. So here there is a plus, here there is a plus, here there is a plus. The rest is correct. Yeah. So now let's go to minimum bandwidth. Minimum bandwidth regenerative code. So when beta now less than or equal to alpha divided by d. Okay, so look at when the beta is less than the alpha by d, then alpha can be reduced without violating the previous equation as I mentioned. So that is this without violating this. So beta now takes a minimum value of alpha by d, then we have an MBR point. So if what you got for every node whatever it has, it gives you little of that, and then you are able to reconstruct it. That's actually minimum bandwidth regenerative point. Alpha by beta, and so using 20 you can get the MBR point. Okay, t is missing again, which corresponds to this. Now that's bit not kind of a thing. So you have to you have to see this one idea. So a little bit careful. So what I can do it here. I'll keep that one 0 to k minus 1. So I should have actually not changed the indices, and I thought I'll unify the two ideas and got into trouble with this indices. So now let's say you have a I equal to 0 to what will happen is so in case of alpha you can use this to get, so for example you take beta takes the minimum value of alpha divided by d, then we have MBR point. So now you apply this equation, that is alpha by d, and you will see this. Do you see this point? So what is really the conditions for at the MBR point? Okay, what's the condition for MBR point at MBR point? So beta should be equal to alpha divided by d. So alpha is equal to d beta, correct? So that also makes sense because at MBR point you connect to t elements and you d beta of bandwidth should be able to collect at alpha. So at MBR point alpha is equal to d beta. Okay, so now you can see that once I get beta, alpha value is simply d times that. Okay, so really the point is to actually see whether we get that one or not. Yeah. So how do you find out the minimum beta for the purpose? Now in case of MBR point, alpha is definitely much more than you actually hold in a, you can so you can say intuitively think of like that. So you have a trade-off curve, the alpha at MBR point alpha, let's say this is the, let's say about this kind of storage, so maybe so there's this bandwidth, so the bandwidth is minimum. So when the bandwidth is minimum, this is a bandwidth, this is a storage, so you have actually alpha is much higher. When the bandwidth is 0, alpha the storage is minimum, correct? So obviously when you have this equation minimum alpha d minus b at MBR point, so you will only get contribution from d minus I times beta. Okay. Okay, but I remember at I equal to 0 you get alpha equal to d beta. So that's what it happens. So you have to really apply. So you remember you can solve this problem if you know this particular series, that is so n equal to what? N into n plus 1 by 2, this is the end one. So let's say if you know this one, you can just apply that and get the result there. So can you see the point? So for example here, so what happens, so every time let's compute at that point b equal to sigma. So when I equal to 0, it is d beta, minimum of alpha plus d beta. So you choose d beta. So I am going to expand this for everything, I equal to 0, 1 up to k minus 1. Let's take I equal to 0. When I equal to 0, it's a minimum alpha, and to I is 0, so d beta. So obviously which will I show? D beta, right? It's because I choose now alpha equal to d beta in MBR point. So d beta plus, d beta is plus, yeah. Then for I equal to 1 to 1, when I equal to 1, it is d minus 1 times beta and so forth. So obviously what it will have is sigma I equal to 1 to k minus 1, you have beta d minus I times beta, correct? So d minus I times beta, I sum over from I equal to 1 to k. Notice that I have a d beta here, okay. So I have here d beta plus So how many things are here? So see, the d beta doesn't have I, so I can take d beta out, and there are k minus 1 of them. So you can say k minus 1 times beta. Okay, then I have minus I sigma I equal to 1 to k minus 1 times I beta. Okay, now I beta is there. Now this is you can take the beta inside here, and it's I. Sigma I equal to 1 to k minus 1 is I. That is same as beta times, so k minus 1 times k plus 1 is k. So it is k times k minus 1 divided by 2. So that is minus, and so you huh?
Second term by dB over k minus 1 times
d beta. So there will be d beta here as well. Okay. So that's what was good. So minus, so that's why if you mix one of them, you will not get the correct answer. Beta into this. Now you appropriately take out. So there is a d beta. So there is a d beta. So you can actually take now 2k. You get actually supply. There is a 2 here now, and that should be equal to b, right? So you can take out 2 common. So shall I can't do it in the back, so it won't visible. So what you get is actually so dB plus d into k minus 1 d is how much? So there is a k minus 1 d, there is a d beta, there is a d beta. So this is just k times d beta, correct? So I should probably, what I'll do, since this one is, remember, this one I'll have to write down here itself, which is same as beta times k minus 1 divided by 2, that's equal to b. I copy down here. Okay. So now this is this now I simplify as d beta times, so k, I can take out this k, and remember it's just k beta, d k beta. Okay, and now take 2 common, so that you will have 2kd minus k times k minus 1 times beta, that's equal to b. So if you want beta, you can take beta is equal to 2b divided by this one. So you get beta is equal to 2b divided by k times 2d minus k plus 1. Okay. So it's a bit slower, but I think you can. So that's what these 2 equations are there. Now in order to set up this trade-off, you probably have to also do bit more work in minimizing it, so that this was so if you want to actually look at the behavior of the curve at the middle points, you have a bit more. So you need to finding the representing the points on the curve, because there could be so many. Let's say if you have here, there could be so many points on this curve. So you need some kind of a change of variables and a little bit of trick you need to do to get hold of that one. So that is explained in the paper. It's a bit more involved, because the problem is also you go up to 0 to k minus 1, and we have some problems that so mathematically it has to be correct, right? So he uses another 2 parameters p. So for example, you should be able to divide alpha into in equal number of steps in order. So you need to have some measure of actually sampling it and looking at what are the corresponding beta that minimizes it. Like, so you choose one set of indices and then choose beta to be minimizing it, and just say how that behaves. So this is the same thing what DeMarquis also did it in the actual, I said the lemma at the proved in the appendix of the paper. So similar kind of thing, but here we just do it only by information theoretic one, and you have a perfect proof you could do. So far that's a clear one. So then once you have establish this, I thought of I do it, but I think this one probably I'll correct it and send it to you, because this is probably neat. These slides, then you can go back over this paper has much more detailed analysis of this storage code, non-achievability. So what happens is that from these condition, this paper, what it does is it shows that there are certain points in this curve that can never be achieved information theoretically, which means that you can actually the code construction can only go up, right? You can't meet those points, so you can't have an optimum one. But fortunately, both MSR and MBR point, it is achievable, and you can actually construct good code. In fact, there are quite a bit of activity around constructing codes at MBR point. So this is the storage one. So this is the so is the bandwidth. So this is the MBR point, and this is the MSR point. So this is storage. Storage. So this should be MSR point. Always it gets correct. So because this is a storage, that's a minimize, and this is bandwidth, this minimize. So it's the MBR point. Okay. So and sometimes the curve will be expressed with the different, but then it looks, you have to follow through that. So you get lots of constructions under this point, lots of construction at this point, and there are not many. And so there was always an open question actually how to construct the codes under that. And so for a while there were a lot of interest in it, and in one important paper came where some points can be satisfied and you have a code, and in another case specifically in some region you cannot satisfy, and so all that results were discussed, and it's a quite involved one. You need a bit more time to actually go through it, but I think with just the lecture that you had from the Adrish on information theory, that one, and using just the basic definition of regenerative code, you should be able to appreciate the results. And so one of the motivations for actually doing regenerative code. So our approach for regenerative code, I already mentioned, it just involves mainly from the building a real coding system. And in that case, what we owed initially was we couldn't do more than one stripe node. So but all the new other constructions are coming, which actually help, forces you to have a much bigger structure, in the sense either you have array code and other stuff. In fact, that's why I gave another paper to you to read today, and so we can probably follow through as a in the coming lecture. What I would like you to go through is just go through it and see, appreciate. You need to be critical of a thing. So sometimes when there are so many papers are there, one of the techniques that you need to learn is to actually see whether that is of my interest to me or not, what problem that it solves, and so how we can approach it. So first you should be able to define that way. So with this background, one of the goals is that you should be able to take any other paper and at least start reading on it. So because we only covered the very basics of storage codes, and there are lots of happening in this area. So at least I hope you should. That's why in this lecture I wanted to also look at the secrecy capacity of the code, but I thought even before that one should be able to at least appreciate the bandwidth and storage things, because we had discussed. And so now that clear, now you can prove that one. So in fact, if you actually also go for the representing the points on the trade-off in a much more careful fashion, so you will actually get a better handle about handling the things. So this was a bit difficult with the previous one, and all in this case it only depends on B, the size of the foil, N, K, D, and alpha, beta. So you can for any particular length you can find a minimum and you can draw yourself. So maybe one technique you can think, you start draw yourself on any drawing software, graph drawing. Okay, we'll see tomorrow.